All right, welcome back, folks. This is a lecture on the hydrolysis of salts. We are in section 6.1 of our book. This is page 340 of our ebook, or 332 of our actual textbook. What this lecture will be about is the fact that salts, or ionic compounds, when dissolved in water, are either neutral, they're neutral salts, the pH of water with the salt dissolved in it would be 7, or that there are acidic salts, salts that when dissolved in water would result in the pH being less than 7, or basic salts, salts that when dissolved in water would make the pH greater than 7. So we're going to talk about how to figure out whether a salt is neutral, acidic, or basic, and a little bit about why as well. I've scrolled down a bit. I'm still on the same page, looking at this text box in green, saying that hydrolysis is the reaction of an ion with water to produce either the conjugate base of that ion and hydronium ions, or the conjugate acid and hydroxide. We've seen these hydrolysis reactions a whole bunch lately. We just haven't called them as such, but this section of our book does. So I just wanted to orient you to hydrolysis. And I'm going to show you a couple of hydrolysis reactions here as I skip ahead. So I'm looking at this orange highlight down below. This is the acetate ion. It's an anion. It's negative, interacting with water, hydrolyzing water, breaking it apart, generating that conjugate acid, acetic acid, and hydroxide. So here's an anion, hydrolyzing water, reacting with water, generating the conjugate acid and hydroxide. Acetate is a base. It's a weak base. And again, when reacting with water, it forms the conjugate acid of that weak base and hydroxide. So if this anion were in water, and we see it generating hydroxide, which it would raise the pH, because hydroxide is being generated. If this anion were paired with a cation that doesn't affect the pH, and that it's soluble with, it would be called a basic salt, because in that ionic compound, in that salt, is a weak base. The anion is a weak base. So sodium acetate would be a great candidate to pair this with to make a basic salt. Skipped ahead, I'm on 335 of the physical textbook, 343 of the ebook, looking at the reaction in green. Here is a cation that is a weak acid. It's ammonium. It's the ammonium ion. Now, if this were in a salt or in a compound, paired maybe with chloride so that it would be totally soluble, the ammonium ion would hydrolyze water, react with water, generating ammonium's conjugate base, ammonia, and hydronium. So again, here is a cation that could be paired with chloride, ammonium chloride, generating the weak base and hydronium. With the generation of hydronium, the pH would be less than 7 were this ammonium ion dissolved in water. Ammonium is a weak acid. And if in a salt is a weak acid, often the pH will be less than 7. We'll talk about times in which it wouldn't. All right, I've gone back now. I'm on 333 of our textbook, 341 of our ebook, looking at this text box here in green. This is about a salt that's neutral. This is about a salt that when dissolved in water will result in a pH being 7. Our book uses phrasing that's great. It's accurate. It just slightly, in my opinion, overcomplicates things. So I will refer to the phrasing of the book, but then I'll be summarizing or paraphrasing for you how I think we're better off thinking about it. So this says a salt containing the anion of a strong monoprotic acid, the anion of a strong monoprotic acid. Remember, there's 6 strong acids. So we're talking about chloride, bromide, iodide, sulfate, nitrate, or perchlorate. So if that's the anion, and it contains the cation of a strong base, remember that's a group 1 or group 2 metal paired with hydroxide, then the salt will be neutral. The pH will not be greater than or lesser than 7. Really what that's saying is that the cation isn't a weak base, the cation isn't a weak acid, and the anion is not a weak base. So if the salt has neither a weak acid as its cation, nor a weak base as its anion, neither of those ions will hydrolyze water, neither of them will generate more hydronium nor hydroxide than there normally is in water, and the pH will be 7. All right, I've just scrolled down, still on the same page, looking at the quick check, looking at number 3, highlighted in blue, which asks you to circle the following salts whose ions will not hydrolyze when dissociated in water. It's also saying which of these are neutral salts. What to you it's saying is which of these salts do not have a weak acid as the cation, nor a weak base as the anion. Take a peek, circle which ones you think satisfy that criteria, come on back and see how your answers compare to mine. All right, I circled rubidium, perchlorate, barium iodide, and calcium bromide, but let's talk about why. This first one would actually end up being an acidic salt. The cation is a weak acid. NH4+ is a weak acid. Chloride, meanwhile, is the anion of a strong acid. So it will not act as a base. Chloride is not a base. Ammonium is a weak acid, so this would be an acidic salt. So that's not going to fulfill our criteria. This one would be a basic salt. Sodium is not a weak acid. / it's the cation of a strong base. / it's a group 1 or group 2 metal. So that will not hydrolyze water. Remember, it stays dissolved in water. It's a spectator. Meanwhile, carbonate is a weak base. It's the anion of a weak acid, H2CO3. So this would be a basic salt because the carbonate will pull some hydrogens off water, generating hydroxide. Well, rubidium is a group 1 / group 2. It's group 1 metal, and it's not a weak acid. So that will not hydrolyze water. It will stay dissolved in water. And then ClO4, 1-, is not a weak base. It is the anion of a strong base, so it is not a weak base at all. This one will be a neutral salt. Fourth one, lithium sulfite. Lithium is a group 1, group 2 metal. It's group 1, so that will not hydrolyze. That'll stay dissolved in water, but sulfite is a weak base. It is the anion of a weak acid, sulfurous acid. Barium iodide will not affect the pH of water. It will not hydrolyze because barium is a group 2 metal / it's not a weak acid. And iodide is the anion of a strong acid, HI, / it's not a weak base. You're not going to see it on a weak base table. It's up there as the conjugate base of a weak acid. Ammonium, methanoate, has a weak acid and a weak base in it, so we'd have to look at the Ka versus the Kb to know whether the pH would be above or below 7, but the ammonium being a weak acid and the methanoate being a weak base means that it will hydrolyze water and the pH would either be above or below 7. Potassium iodate will hydrolyze water. Potassium won't. It's a group 1 metal. It's not a weak acid, but iodate is a weak base. It's the anion of iodic acid. Cesium fluoride will hydrolyze water. Cesium won't. It's not a weak acid, but fluoride, F-, is a weak base. It's the anion of HF, hydrofluoric acid, which is a weak acid. And then calcium bromide is our last candidate. This is not a weak acid, calcium, nor is bromide a weak base. / calcium is a group 2 metal, the cation of a strong base, and bromide is the anion of a strong acid, HBr. But neither is a weak acid nor a weak base. So those are the 3 salts that will remain neutral in water and that will not hydrolyze water. So that was about neutral salts. We're now looking, and we're on the same page now. We've scrolled down at this section titled Basic Salts. And this is the reaction we saw at the beginning of the acetate ion hydrolyzing water, forming its conjugate acid, acetic acid, and hydroxide. The generation of that hydroxide would cause the pH, if acetate were dissolved in water, to be greater than 7, a basic salt. All right, I've flipped a page. I'm at the top of 334 in our textbook, and this is a continuation of basic salts. So our textbook says, again, a little wordy, although it's good, a salt containing the anion of a weak monoprotic acid, meaning a weak base, right? A salt containing the anion of a weak monoprotic acid means it has a weak base in it. And the cation of a strong base, meaning it doesn't have a weak acid in it also. It just has a weak base as the anion, will produce a basic solution in water because the anion acts as a weak base. So if in a salt, the anion is a weak base, or if in a salt you see a weak base, you know that the salt, when it dissolves in water, will cause the pH to be above 7. And we'll do some calcs shortly to figure out what the pH would be. All right, same thing. We're going to do quick check 2 here in green. You're going to circle, and I won't spend quite as much time justifying my answers as I did last time. Circle which of these salts you think will produce a basic aqueous solution. What you're looking for is the salts that have anions that are weak bases, or that aren't the anions of a strong acid, is another way to think of it. Here I got 3 up top and 3 down below I circled. I've left out aluminum bromide, rubidium perchlorate, that chromium nitrate, and then iron iodide. I left those out because their anions, bromide, perchlorate, nitrate, and iodide, are not weak bases. Or, if you want to think of it this way, they are the anions of a strong acid. Hydrobromic acid, perchloric acid, nitric acid, hydroiodic acid. The rest of these have anions that are weak bases or aren't the anions of strong acids. All right. We're looking now at sample problem 661 on that same page where we're going to calculate the pH of a basic salt solution. you should see that this looks fairly similar to the weak base problems or weak acid problems, because those are similar to each other we've solved in the past. All right, let's walk through this. We got a 9.54 gram sample of magnesium cyanide. That would be a basic salt because CN is a weak base, or it's not the anion of a strong acid. Dissolved in enough water to make a 500 milliliter solution. We want to calculate the pH. So the first step is we need to convert the mass of magnesium cyanide to moles. Dividing by the molar mass does that. And then at the same time, divide that by the volume in liters, 0.5 liters. We get 0.25 molarity for the magnesium cyanide. But because it's completely soluble, from each magnesium cyanide, we will generate 2 cyanide ions. So the concentration of cyanide of the weak base is 0.5 molar. 0.5 molar. All right, this is a weak base. Our book expects that we go to page 277 to get the Ka for HCN. And remember, Ka times Kb is Kw. So this is our book converting the Ka for HCN, 4.9 times 10 to the minus 10, to the Kb for Cn minus. So Kw over the Ka for HCN will be the Kb for Cn minus, 2.04 times 10 to the minus 5. Again, if this were an AP problem, we'd likely be given the Kb in this problem, or possibly the pKb, more likely the Kb, so you could skip that step. But if you weren't, here's how it would go. So we write the interaction of cyanide, this weak base, with water, which generates the conjugate acid, HCN, and hydroxide. We either leave water out of our ice table altogether or we cross it out. We know from above that cyanide is 0.5 molar. There's never product to begin with. They're both 0. Cyanide goes down by X. Our products, our conjugate acid and hydroxide, go up by X. And we get 0.5 minus X and X in that third row. Remember, X being small compared to 0.5 means we assume 0.5 minus X being 0.5. So we set Kb equal to our E row, our equilibrium row. Kb will equal X squared over 0.5, which we've seen a bunch now. And if we solve for X, which is the concentration of both the weak acid and, more importantly, hydroxide, we get 2.04 times 10 to the minus 5. Well, if we take the negative log of hydroxide, we get POH. The negative log of hydroxide is 2.496. And if we're asked for pH, which we are, 14 minus POH is pH, and that gives us 11.5. So, again, a fairly similar looking problem to what we've done in the past. We're just talking now about a salt generating the weak base, as opposed to the weak base itself being added to water. And because salts are solids, we tend to start with the mass of a salt, as opposed to if it were a weak base already dissolved in water, we would maybe already start with the molarity. So that's really the only difference, once you figure out how they go. All right, I've skipped to the next page, 335 of our physical book, 343 of our ebook, looking at practice problem 661 here, basic salt solutions. And I'd like you to try this third one highlighted in orange, this third one on your own. Please give this one a shot and come on back and see how your answer compares to mine when you're done. All right, my solution's all over this whiteboard, so hopefully I can help you navigate my solution as we go through it. So here's the sodium methanoate, which is a completely soluble salt because sodium's a group 1 metal, so it'll completely dissociate. Rightward pointing arrow. Sodium ion spectates. It is not a weak acid, / it's the cation of a strong base, so we ignore it. Really, we're dealing with the methanoate ion, this weak base, Notice I said star, parentheses, weak base. That weak base will then hydrolyze or interact with water, forming the conjugate acid of that weak base, methanoic acid and hydroxide. And it's these hydroxide ions that will ultimately bring the pH above 7, which we know it to be, 9.2. I wrote the Kb expression for this, so it's the conjugate acid times hydroxide over the undissociated or the original concentration of weak base. This is a book problem, so I wasn't given the Kb or the Ka, so I go to page 277 and find the Ka for HCOOH, the conjugate acid of this weak base. It's 1.8 times 10 to the minus 4. I know Kw divided by Ka is Kb, so this is getting Kb for this weak base, so we can use it in our ice table in a bit. 5.56 times 10 to the minus 11 is the Kb for HCOO minus. The next thing I did was converted the pH to the POH because this is a weak base problem and I know I've got to have hydroxide in my ice table, not hydronium. 14 minus pH, or 14 minus 9.2 is the POH, 4.80. Now I want to get hydroxide concentration, so I can put it into my ice table in the E row. 10 to the negative 4.8, which is the concentration of hydroxide, is 1.58 times 10 to the minus 5. All right, so if we look at my ice table, We don't know the original concentration of the base. That's what we're trying to find. There's never original concentration of conjugate acid or hydroxide. But because I know the concentration of hydroxide at equilibrium from the pOH, I plug it in here. And these two values are always the same. Therefore, they go up by that amount, and the weak base goes down by that amount. But again, this is a very small value compared to X, so we say that the initial concentration of weak base equals approximately the equilibrium concentration of weak base. So I plug that into my Kb expression. I've got hydroxide times conjugate acid over X equaling Kb. They are the same as each other, so I got 1.58 times 10 to the minus 5 squared over X equaling Kb. And when I set that equal to Kb and solve for X, I get 4.52 molar as the final answer, or the concentration of the weak base that resulted in this high pH, this pH above 7. All right, so we're on the same page. We've scrolled down. We're on 335 of our textbook, looking at acidic salts, the third type of salt. We talked about neutral salts, basic salts. These are now acidic salts. Again, we saw this reaction earlier at the start of the lecture. This is ammonium. It's an ammonium ion, and it is a weak acid. When it reacts with water, it'll form ammonia, the conjugate base, and hydronium. And it's this hydronium that will ultimately drop the pH, making the salt acidic. Remember, ammonium has to be paired with an anion that itself isn't basic. These are going to be the anions of strong acids: bromide, chloride, iodide, nitrate, perchlorate, or sulfate. So, all right, our book says a salt containing the cation of a weak base and the anion of a strong monoprotic acid. In other words, a salt that contains a weak acid and doesn't have a weak base also, that just has a weak acid as its cation, will produce an acidic solution of water because the cation, as we see above in green, acts as a weak acid producing hydronium, and the anion does not react. The anion doesn't react at all with water. All right, scroll down the page looking at sample problem 612, calculating the pH of an acidic salt. This is going to look and sound familiar, as it's quite similar to the sample problem for the basic salt. Again, we're just going to see a pH here in the end that's less than 7. So here is our salt, C5H5NHNO3, dissociating. It's got nitrate as its anion, so it completely ionizes, completely dissociates, such that the concentration of the salt will be the concentration of the weak acid, of the cation. It's a 1-to-1 ratio. Wrote the Ka for that weak acid, and we know the Kb of the conjugate base. It's given to us in our problem, so we have to use Kw over Kb to get Ka. Instead of being given Ka, we were given the Kb of the base. Just a little extra fun step in there. So the Ka for this acid is 2.13 times 10 to the minus 6. We know the initial concentration of the acid is 0.1. Both products are 0. Acid goes down by X. Products go up by X. 0.1 minus a negligible X, once again, is 0.1. So we get Ka equaling X squared, once again, over original concentration. If we plug in the Ka, which we know to be 2.13 times 10 to the minus 6, and solve for X, which is significantly the concentration of hydronium, we get 4.61 times 10 to the minus 4. And if you take the negative log of that, you'll get the pH of the solution at 3.34, less than 7 as we expected. I flipped my page. I'm on 337 of our physical book, looking at practice problem number 1, highlighted in green. So same thing, give this one a go on your own. Notice that you're given the mass of the salts. You'll have to convert that to moles and then use the volume to find molarity, because oftentimes salts are given to us in masses because they're solids, and then it'll look fairly similar to what we've seen so far. So give this one a shot. All right, there was a lot going on in that problem. Hopefully you enjoyed yourself solving it as much as I did. All right, so first thing that I did was I wrote the dissociation equation for ammonium nitrate, which is a rightward pointing arrow because it's got nitrate and ammonium. Those are both very soluble ions, so again, complete dissociation. I then showed the ammonium interacting with water. It's the ammonium that is the weak acid in this salt. Remember, nitrate is not a weak base. It is the anion of a strong acid, nitric acid. So it's ammonium that we're focused on in this problem. Interacting with water, forming ammonium's weak base, ammonia, and hydronium. I've then written the Ka expression for it because I know I'm going to need it at some point. It'll be ammonia 7 in my book. I got the Ka there, which again, if this were an AP problem, would be embedded within the problem. Then I took the mass of ammonium nitrate, divided it by its molar mass to get moles. 0.200 moles is what I got. And then when I divided that by the volume, 500 milliliters or 0.5 liters, I got 0.4 molar ammonium nitrate. Since there's just one ammonium ion for each ammonium nitrate, the molarity of the salt is the molarity of the ammonium ion also. Here's my ice table. 0.4 molar ammonium I start with, no hydronium nor conjugate base to begin with. Ammonium x hydronium and ammonia go up by x. 0.4 again, minus negligible x is 0.4. So once again, we're seeing this Ka expression equaling x squared over the initial and equilibration of, in this case, the weak acid. So I've set that equal to the Ka, which I get from page 277. 5.6 times 10 to the minus 10 is the Ka of NH4+. And when I solve for x, which is both the concentration of hydronium and the conjugate base, but to us it's the concentration of hydronium, I get 1.5 times 10 to the minus 5 molar. Well, I want pH. So when I take the negative log of that value of 1.5 times 10 to the minus 5, I get 4.82. So there is the pH of this solution that contains the acidic salt that had NH4+ in it, that weak acid, causing the solution to have a pH less than 7 and be slightly acidic. All right, almost done here, folks. We are now on page, where are we? 339 of our textbook, looking at this section here titled Salts Containing Weakly Acidic Cations and Weakly Basic Anions. We've looked so far at salts that don't have a weak acid or a weak base as their cation or anion. They're neutral. Or salts that have as the cation a weak acid, but the anion is not a weak base. It's an acidic salt. Or salts that have as the anion a weak base, but the cation isn't a weak acid. It's a basic salt. Well, if the cation is a weak acid and the anion is a weak base, then those salts can either be acidic or basic, or possibly neutral, but unlikely. I flipped my page. We're looking at this text box here that I didn't make a pretty color. Oh well. And this is the rule of thumb. Fortunately, you don't have to deal with these mathematically. We just look at them qualitatively. So again, we're talking about a salt whose cation is a weak acid and whose anion is a weak base. Well, if the weak acid is stronger than the weak base, if the Ka for the cation is greater than the Kb for the anion, it'll be acidic. Acid wins out. Meanwhile, if the Ka for the cation, if the Ka for the weak acid is less than the Kb for the anion for the weak base, it'll be basic. And if they happen to be equal, they both have to be 10 to the minus 7, because remember the product of them is always 10 to the minus 14, then the solution will be neutral. But that would be very coincidental. So again, you won't have to do math on these. Rather, just figure out whether the Ka or Kb is greater, and then whether it's acidic or basic. Actually, one more small thing. To bring this back to the titration concepts and graphs we were looking at earlier, if you recollect that when you titrate a strong acid against a strong base, or a strong base against a strong acid, the pH at the equivalence point is equal to 7. And that's what my sort of lousy blue graph over there is saying, is the pH at the equivalence point equals 7. Well, that's because the salt that's produced, in this case sodium chloride, has neither a weak acid as its cation nor a weak base as its anion. / its cation comes from a strong base and its anion comes from a strong acid. So pH equal to 7. Meanwhile, if we titrate a strong base against a weak acid, remember the pH doesn't start as low, there's an initial bump, then it kind of starts to climb slowly, then it climbs fast, but over a narrower range. Anyways, the pH at the equivalence point here is greater than 7. That's because the salt that's made, sodium acetate, when it dissociates, has as its anion a weak base. The CH3COO- from this salt is a weak base, making the pH at the equivalence point greater than 7. If we go then to a weak base, strong acid, here's ammonia reacting with HCl. We form ammonium chloride, no water this time. Ammonium, NH4+, is a weak acid. It'll hydrolyze water to make hydronium, and the pH will be less than 7 at the equivalence point. So just wanted to bring that up in the context of titrations. That is it, folks. Splendid job thinking, taking notes, doing those practice problems on your own, comparing your answers to mine, and hanging in there and having a great attitude. Remember, be kind to yourself and to others, work hard, try to make the world a better place. See you soon.